What's good, everyone? In today's video, we're going to be taking a look at projectile motion. We'll be expanding our knowledge base into 2 dimensions. So the previous couple of videos, everything that we did was in 1 dimension. So all the problems that we looked at and all the equations that we derived and used were only able to be used in 1-dimensional problems, solving 1-dimensional kinematic equations. In this video, I'm going to show how we can expand into 2 dimensions. So solving more complex problems in a 2D plane, projectile motion problems where position, velocity, and acceleration perhaps are in more than 1 spatial dimension. So before we were treating x not really as a vector, just as a scalar, but in reality it's a vector, and perhaps it's made up of multiple components in different spatial dimensions. So let's say x is 1 dimension and y is another dimension. It's at a 90-degree angle to x. So everyone's familiar with this. If this is x, then this is y, and the 2 dimensions make a 90-degree angle with each other, and they form the 2-dimensional plane that we're drawing on right now. So I should never erase that. If we have a coordinate system x and y, and there's some dot at a random position in the plane, this dot has a position x comma y. So it's a 2-dimensional position. This is going to allow us to solve more complex physics problems, things that we would see more in everyday life, in real life. So if x is a vector, it can be broken up into components, I hat and j hat, which are just unit vectors that are perpendicular or orthogonal to each other, and x and y are their respective magnitudes in those directions. So same thing applies before. We can still do calculus with vectors. So if we take the derivative with respect to time, we still get the velocity, but the velocity is also a vector, right? And maybe that has components vx in the I hat direction and vy in the j hat direction. So if the original vector has 2 components, then taking a time derivative, it's just another vector. It still has the 2 components in the same dimensions as the original vector. It's just it's a linear operation. Doesn't change anything about the vector, the direction of the vector. So if we go to our kinematic equations, let's say they were x equals x naught plus v naught t plus 1/2 at squared, and vf squared equals, okay, xf. In this case, the naught means initial. So in previous videos, I used notation x sub I, v sub I, meaning the initial velocity and position. Now I'm choosing naught. It means the same thing, the initial, and f is final. Final velocity squared equals initial velocity squared plus 2a delta x. Let's see, there was final velocity is equal to initial velocity plus acceleration times time, and then the last one was delta x is equal to final velocity plus the initial velocity times time divided by 2. So these are all 1-dimensional, but if I allow x to be a vector and velocity to be vectors and acceleration to be a vector, because they're just derivatives of position, allow them all to be vectors we can split them up. We can split them up into their respective component forms. So so we're going to go from one dimension to two dimensions. If we allow position, velocity, and acceleration to be vectors, they might have components in more than one spatial dimension. So we can break them up into their component forms and treat each dimension as independent and solve things independently. So if x is a general position vector, again with components x in the I hat direction and y in the j hat direction, then we can break this up into x equals, and now there's no vector, there's no vector arrow on top because these are the components of the vector. X is equal to x naught plus v naught x t, the x component of the initial velocity, plus 1/2 a x t squared, the x component of the acceleration. So if this is x and this is y, the acceleration is some vector in that plane. It may have a component pointing in the x direction and a component pointing in the y direction. This is only the x component. This turns into, y now equals y naught plus v naught y t plus 1/2 a y t squared, vf x squared equals v naught x squared plus 2 plus 2a x delta x, and also vf y squared equals v naught y squared plus 2a y delta y. This one will turn into v f y equals v naught y plus a y t, and vfx equals v naught x plus a x t. And one more, delta x is equal to, this is just the change in position in the x dimension, vf x plus v naught x t over 2, and delta y equals vf y plus v naught y t over 2. So these are the four kinematic equations now broken up into their respective component forms. And the equations are independent in each dimension. So we can solve just so say we only know information about a ball flying through the air. We only know its information in the x direction. So it's launched at a certain angle, and we know that it goes a certain distance in x before it hits the ground, but we don't know the maximum height it reaches in the y dimension. If we know certain information, we can use just the x equations, solve for time, plug it into the y equation, and then get the maximum height, something like that. The component forms of the equations are independent. We can utilize both of them to get the information that we need. So from here on out, I'm going to use naught as the initial position, and x will only be the x component of the position vector, and y will only be the y component. I'm no longer using x for the general vector, general position vector. I'm using it only as the x component. So xf equals x0 plus vx, v naught xt plus 1/2 a t squared. Something very important in projectile motion problems. Let's say there's a table, here's the ground, there's a table, and a ball is launched at a certain angle theta with respect to the horizontal. There is some, so if we zoom in on this v naught vector, there is a component in the y dimension and a component in the x dimension. This is v naught x and this is v naught y. They're perpendicular. They're perpendicular, and the vector makes an angle theta with respect to the horizontal. Now, if we move this v naught y component over here, you see that we can form a triangle, a right triangle. Again, here's theta, form a right triangle. We know what this is, v naught. We know what this is, v naught y, v naught x, and we have theta. Some basic trigonometry. We can rearrange this so we know that, remember, SOHCAHTOA, sine is opposite over hypotenuse, so sine theta is equal to opposite v naught y over the hypotenuse. V naught, let's swap v naught and sine. Sorry, no, let's not do that. Let's multiply both sides by v naught and solve for the y component, equal to the vector times sine of that angle. And also cosine theta is equal to adjacent over hypotenuse, v naught x over v naught, multiply both sides by v naught, we get v naught cosine theta is equal to v naught x. Awesome. So perhaps there's a problem where we're given the information of the magnitude of v naught and the angle, but we need, in order to solve one of these equations, we need v naught x. If we know the angle and we know the magnitude of the vector, we can solve for one of the components using these equations right here, just using basic trigonometry. Something else that's important is in real world problems, gravity points downwards and it accelerates objects downwards. It's an acceleration. Generally, there's no acceleration in the x dimension, so gravity is acceleration in the y dimension. Gravity does not accelerate things horizontally, only vertically. So generally in real life, the acceleration in the x direction is 0. Usually things do not accelerate like this, at least not from gravity. In real life, things do slow down or speed up horizontally. Air resistance slows things down. Brakes from a car slow things down horizontally, but in terms of, simple problems that you'll see in high school or college level physics, early college physics classes, generally you ignore air resistance. So 99% of the time, the acceleration in the x direction is going to be 0. So keeping in mind what I just said, that 99% of the time in projectile motion problems, acceleration in the x direction is negligible. There is nothing accelerating things horizontally. This equation has the final term go to 0. So usually the x component of the velocity remains constant in projectile motion problems. So we can simplify the second kinematic equation to the final position in x is equal to the initial position in x plus the initial x velocity times time. And I just said a few moments ago that the acceleration in the y direction is, of course, gravity. So this becomes final y position is equal to the initial y position plus v naught yt minus 1/2 gt squared. Here are two of our projectile motion equations. It's easy to see. Let's go back to our first one. Vf equals v naught plus at. Like I said, acceleration in the x direction is often 0. So this would be 0 for x, saying 1 equals 1. It's tautology. It's not very useful. However, if we take the y components, still applies. Ayt is equal to v naught y minus gt. So Vfy equals v naught y minus gt. Same reasoning with Vf, v naught squared 2a delta x. For the x component, the acceleration is 0. Again, that's saying 1 equals 1. But if we do the y component, it tells us some information. Delta y. Yes. And then the fourth one, delta x equals v naught vf plus v naught over 2t. There's no acceleration in the x direction. Vf and v naught are the same thing. It's 2 v naught over 2 equals v naught t equals delta x. That's the exact same thing as this equation right here. No new information is gotten from there. But if we take the y component, vfy, v naught y, this tells us something new. So 1, 2, 3, 4, 5 equations now instead of 4. And then there's a secret equation that I'm going to derive now too, called the range equation. So I put the 5 equations that we just derived right here, and then there's a special range equation as well. The way we get that is, let's start with the horizontal equation. Xf is equal to x naught plus v naught x t. If we select our coordinate system, if we select the origin of our coordinate system properly, you can always make x naught and y naught 0. So let's just assume that we did that, and we get the final position in x is equal to v naught x t. Remember earlier, using basic trigonometry, we found that the x component of the initial velocity is nothing more than the initial velocity times sine of the angle the vector makes with respect to the horizontal. Let's substitute that in for v naught x up here. We get x is equal to v naught sine theta t. And then if this is the total the total amount of distance traveled in the x direction, let's call that the range. So whatever projectile we launch, the maximum distance it goes in the x dimension before landing, before stopping, landing. Let's call that the range R. So I'm just calling the variable something different. Now let's say, so if I launch something, let's say I launch a ball, right? It's gonna go, here's the ground, I launch it from the ground. If I select my coordinate system here, 0, 0, x naught is 0, y naught is 0. Here's R. The final y position and the initial y position are both 0, and they're equal, right? So I launch it from 0, which is the ground, and also where my origin of the coordinate system is. And then it comes to the same height in the y direction at R. So let's use this. Y f equals y naught equals 0 when x is R. Not at every point in time, but when x is R. And that's equal to v naught y t minus 1/2 g t squared. What is v naught y? V naught y is nothing more than v naught cosine theta, as I showed earlier. Matter of fact, let me add those. Excuse me, I made a mistake. So this is cosine. Yeah, cosine goes with the x component, of course. Cosine. Cosine goes with x. Cosine theta is adjacent over hypotenuse v naught x over v naught cos theta equals v naught x. Yeah, so cosine goes with x, of course, and sine goes with y. So let us replace this v naught y with v naught sine theta. So this is v naught sine theta minus 1/2 g t squared. So I just erased and moved them up here, but this is where we are. And then this is 0, we can bring this term to the other side. V naught sine theta times time is equal to 1/2 g t squared. One of the times is going to cancel. Let's solve for t. 2 v naught g 2 v naught over g sine theta is equal to time. Let's plug this in up here, and this is R is equal to v naught cosine theta times 2 v naught over g sine theta. Let's rearrange this a bit. V naught times v naught is v naught squared. 2 v naught squared over g. Cosine theta times sine theta. There's an identity somewhere. Cos theta sine theta is equal to sine of 2 theta. That's a trig identity. Feel free to look it up. I swear to God it's true. It's equal to sine of 2 theta. And that's equal to R. Call this the range equation. Twice the initial velocity squared divided by gravitational acceleration times sine of twice the angle that the initial velocity makes with respect to the horizontal is equal to the total range that the object projectile travels in the x dimension. This is something that's true. I will add it to our box on the right, to our box over here. So using these equations, we can pretty much solve any projectile motion problem. In the coming videos, I will show how to solve some basic ones and then some more complex projectile motion problems. And then we will move on from there. Thank you for watching.